Okay, I'm here to help you with Lab 6, and we'll go through these one by one. And so do the work. I'm here to help you. I don't want to do the lab for you, and also it won't benefit your learning. So as much as possible, do what I ask you to do before you see the answer. So look at the situation. Lab 6, number 1, is problem 5.1 from the Phizlets. And you'll see a red book against a wall and a hand holding it. So draw a rectangle for the book and show all the forces acting on it. That's the free body diagram of the book. Do that right now. So you should have 4 forces. I'm showing those. Make sure you have 4 and label what each force is. Okay, those are the 4 forces. You should have all of them. The applied force, which is the hand pushing the book against the wall. When the hand pushes the book against the wall pushes back with a normal force, an F norm or an Fn, that's equal and opposite. Why is it equal and opposite? Because the sum of the forces in the x direction has to be 0, because there's no acceleration. In the y direction, we have the friction force, always acting parallel, in this case parallel to the wall. That's what holds the book up. And the earth pulling down on the book, F grav, Fg, or Mg going down. And notice I wrote the F fric. I write it in a shorter form, or what friction is always equal to, mu times the coefficient. It's important to recognize here that there are 2 mu's, static and sliding. They have different values. And in this simulation, we're going to calculate how much force it takes to hold it stationary. That will be static friction. And how much force it takes as it slides down the wall. And when it slides down the wall, when you play the animation and you watch it slide down the wall, you do have to check whether it's accelerating or not. Okay, now in this case you're asked to do the general symbolic solution. So the way you do that, try and do it, is to use your free body diagram, write some of the forces in the x direction, some of the forces in the y direction, take those 2 equations and derive a general symbolic solution. So try to do that. And get as far as you can before you look at what I'm going to do next. Okay, before you look at the details, pay attention to the general problem-solving strategy that I'm showing you and that you want to learn. This is a very powerful method for solving a wide variety of problems. So on your equation sheet, you'll see a list of steps that you use in problem solving, and I'm showing you that here. The diagram is given. That's in the simulation. What we've done is the next step is we drew a free body diagram of the situation that we're trying to deal with. Then the next thing is we do sum of the forces x and y, and we use our free body diagram to write out these 2 equations. So we look at the sum of the forces in the x direction, and we recognize that there's no acceleration in the x direction, and we see there are 2 forces. The applied force, the normal force is negative. They're going to be equal to 0. So the magnitude of the applied force is equal to the magnitude of the normal force. And the applied force is what we want, so we need to find out what the normal force is. So we go, we go to the sum of the forces in the y direction. And for both cases, holding the book steady against the wall and holding the book as it slides down at a constant velocity. And when you look at the simulation, you do need to verify that it is sliding at a constant velocity. Otherwise, this would not be 0. So in this simulation, in these 2 cases, we have that the friction force, which is positive, minus the force of gravity, which is negative. I put the negative in, equals 0. And so the friction force is mu kFn. The gravity force is mg. And when I solve it, I get that the normal force is equal to mg over mu. And since the applied force is equal to the normal force, this is the general solution of the applied force. What's the difference between the two situations? The mu is different. So when we're holding it stationary against the wall, the mu that we use is the static coefficient of friction. And when we're holding it as it slides down at a constant velocity, such as the acceleration 0, the mu is the kinetic or sliding friction. Now we move to Lab 6, Problem 2, which is Vislit Problem 5.2. And when you look at that, you'll see that the situation is the same. In a general sense, the free body diagram is the same. But when you go and run the simulation, you'll see that it appears to be accelerating. So how do you find out, A, if it's accelerating, B, what the acceleration is, and C, is the acceleration constant? And if that's the case, and you will find out that it is accelerating and the acceleration is constant, then the free body diagram remains the same. The hand pushes on the wall pushes back, friction acts this way, and the gravity force acts this way. The only difference is these two vectors are no longer equal. Which one is bigger? Well, the acceleration is down, so that means the gravity vector is now larger than the force in the opposite direction, the friction vector. And so how does that affect? Nothing changes here, right? The acceleration in the x direction for this new case is still 0, but in this case the acceleration is no longer 0, so we have to fix that. So we take out the 0, and we put in m AY. And you have to find the AY. We'll talk about that in a minute. How do we find the AY? You should be able to do that. But so now I write m AY. And so what we want is the normal force, right? Because the normal force is the applied force, and that's what we're trying to find. What's the applied force in this case? So do the algebra and solve for the normal force and simplify the expression as much as possible. So pause the video and do that. Don't just watch me. Do the algebra. You need to practice your algebra. So there it is. There's a few things to pay attention to, though. So remember, G is 9.8. It's not negative 9.8. So I put the negative sign here because this is down. And AY could be positive or negative, so I put the negative sign in, meaning that I'll just put the magnitude in. You could do it leaving it positive and then put a negative number in, but this is how I like doing it. So when I add mg to both sides, I get mg minus may, putting the negative sign here. And then I factor out the m and get mg minus ay. And when I divide through by the mu k, the kinetic friction, I get that the applied force is the Fn, and in this case it's mg minus ay over mu k. It looks almost like the other one, only now there's an acceleration, so that's included in the general solution. So this is the general solution for this problem for any mu k and any ay. Okay, now we want to get the ay. That's a kinematics problem. Go to your equation sheet, second row, top, look at the four kinematics equations, and pick the one that you think will be appropriate in solving for AY in this problem, and then come back. All right, there's more than one way to do this, but I think the easiest way is to choose the third equation. I usually call it equation 3. On your equation sheet it's written in X, but we're in Y, so I rewrite it in Y. So delta Y, Vy initial t plus 1/2 AY t squared. The Vy initial, it starts from rest is 0. And so when I solve for AY, I get 2 delta Y over t squared. Now, you might not check, but you should, is the acceleration constant. So do this for 1 second, do it for 2 seconds, or do it for the whole time, 4 or 5 seconds, whatever it is. And if the acceleration is constant, you should, over any time and distance interval, get the same AY. You should absolutely check that just to be sure the acceleration is constant. And now we're done with problems 1 and 2. Okay, whoops, I forgot the 6. Lab 6, problem 3. Question 3, problem 5.4 in the Phizlets. So anyway, see if you can do this on your own. This is a good, challenging problem. This is the process you're going to use. But if you don't know how to get started, draw the free body diagram. Then do sum of the forces. And then come up with your general solution. So do as much of that as you can before you see how I do it. Okay, so you watched the simulation, I hope. I didn't mention that. And so you're aware of the situation. It goes for, I think, 2 seconds at a constant velocity, and then the force doubles, and it goes for another 3 seconds with an acceleration. And so the free body diagram, there should be 2 of them. So in the first case, the applied force and the friction force are equal, and the normal force and the grav force, the force of gravity, are equal. There's no acceleration in either direction. In the second case, there's an acceleration, not surprising because the friction force isn't going to change, because the mu coefficient of friction doesn't change and the normal force doesn't change. Only the applied force changes, so now the force is unbalanced and it's going to accelerate. So you're always looking for whether there's an acceleration or not, because that's what you need to know. You need to know the forces, and you need to know whether there's an acceleration or not when you write the equations. Okay, so the diagram is the simulation. The 2 free body diagrams are given. So the next step is to write down some of the force equations. So you have sum of the force X for the first free body diagram, sum of the force X for the second free body diagram, and the sum of the forces in the y direction are the same for both. And so write those out, those 3 sets of equations, and then by combining those 3 sets of equations, you should be able to come up with the answer for mu k for this problem. That's what you're looking for, mu k. So see if you can do that on your own before you watch me. So I'm urging you not to just watch, because you'll never learn it if you just watch. You've got to push yourself and try and do this on your own. But if you're lost at this point, here's what you do. So notice we did the free body diagrams, sum of the forces. We're just using this method. That's the way to solve problems. Even if you don't know where it's going, you just do it and kind of like see the solution along the way. So for this one, we have F applied equals the friction force equals 0 because the velocity was constant. And so the applied force is equal to the friction force, which is mu k Fn. In this case, we have 2 times the applied force minus the friction force, equals this in acceleration, so max, it's not 0. And so since the applied force, now here's where I do the algebra. Oh, and then also for the y direction, Fn equals the force of gravity, or mg. So now I got to substitute out because I have these things I don't know. So the applied force is mu k Fn. So where it says F applied, I put in mu k Fn, and I get 2 mu k Fn minus the force of friction, mu k Fn. So 2 mu k Fn minus mu k, the algebra, right, leaves you with mu k Fn, and that's equal to max. And so mu k is simply max divided by Fn. And Fn is equal to mg. So we have max over mg, leaves us with the very simple solution ax over g. That's what mu k is, ax over g. And it makes sense because these both have units of acceleration, and so mu k should have no units, and this would just be a number with no units. Getting ax is easy enough in this case because you have the velocity given to you and the time, and so you can simply do change of velocity over time. But good practice is do it for 2 different intervals at least to make sure that the acceleration is constant and make sure you're getting a consistent value that you have confidence in. So we'll skip over lab 6, question 4, which is 5.5. I think you can handle that. And we'll move ahead to the 5th question on lab 6, which is simulation problem 5.6. So take a look at it. The simulation itself is the diagram. Draw the free body diagrams. There'll be 2 of them. Do some of the forces and then use algebra to get the solution. See if you can do it on your own. This is a good time to start practicing what we've been learning. So getting the free body diagrams correct is really important, right? Because when you do the sum of the forces, you're not going to get that right if you don't have the right forces. So for the red block, we have the force of gravity, mg. We have the normal force up, and we have the green block pressing down on the red block. And since there's no friction with the surface that this is on, the way in which the green block is pushing the red block is through the force of friction. So the force of friction between the red block and the green block shows up as the same force. That's a little bit tricky. In other words, as we slide this block, the red block is exerting a backward force of friction. The red block is pushing back on the green block, but the green block is pushing forward on the red block, and that's why this accelerates. So this is the 2 free body diagrams, and then you have as many as 4 different equations. Some of the forces x and y on each one of these. But the net force on the red block is simply its mass times its acceleration, and we know its mass, and you can calculate its acceleration, so that's easy. And the net force on the green block is simply its mass times its acceleration, and so you can get that. But the applied force is the friction force minus the applied force, or since this is all going negative, if we consider this positive, the applied force minus the friction force is going to be the net force. So to find the applied force, you have to find the friction force. But to find the friction force, you can do that over here because it is the only force acting. The force of friction is the only force acting on the red block, and so the net force on the red block is the force of friction. And then you come back here, and I'm going to consider this positive, F applied minus F fric equals ma, right? The a and the, I'm just reversing the direction. And so the F applied then is simply the net force, max, plus the force of friction. Okay, that should take care of that one. All right, the last problem is number 6 on the lab. Well, it's number 7, the last simulation, and problem 512, and it shows a disc with a coin that rotates. And so you should run the simulation and convince yourself that it moves at a constant speed and find out what the velocity is. And then knowing the velocity, find the acceleration, and then do a free body diagram of the coin, and then use some of the forces to find the minimum coefficient of friction so that the coin doesn't slip as the thing spins around, right? So it doesn't slip off. All right, so to get the velocity, you want to do the circumference of the circle divided by the length of time it takes to go the circumference. And you could do a quarter circle or a half circle, but you might as well do a full circle. And or you could do 2 circles. I think it goes for more than 2 turns. And then once you have the velocity, and you can see that it's useful to observe that it takes a quarter of the time, half the time, 3/4 of the time, just so you know that the velocity is constant. And then the centripetal acceleration, you just square the velocity and divide by the radius. So the key thing here is going to be the radius, because you're going to measure that. So make sure you measure from the center of the circle to the center of the coin. Or another way of doing it is get the position of the coin here and let it go to the other side, and then measure the position of the coin, and that will give you the diameter, right? Because it's not the diameter of the disc, it's the diameter that the coin, of the circle that the coin is moving in. And when you have an extended object like a coin, you always measure to its center. And the advantage of doing it from one side to the other is you don't have to find the center of the circle. And you would expect that to be 0, 0, but it might not be exactly that. So if you don't get the right R, all these numbers are going to be wrong. Anyway, once you have that, you can get the acceleration, then we draw the free body diagram. And from this view, we can only see the force keeping it on the center, the centripetal force, and that is friction, right? Because if this were frictionless, when the thing spun, the coin wouldn't move. And so it is static friction. But we need to look at this along the line, along the horizontal plane. So if I take the coin and I draw it along its edge, then I can see the gravity force, the normal force, which is the platform supporting the coin, and the force of friction acting toward the center. And since the force of friction is mu s Fn, remember, S, static friction, to get mu s, we look at the sum of the forces in the x direction. If we call this up and down y and horizontal x, so we would have sum of the forces in the x direction equal max. And you see there is only one x force, and that's the force of static friction. And that's equal to the mass times the acceleration, but of course the acceleration, we found it is v squared over r. And the Fn we get, right, by looking at the sum of the forces in the y direction, as we always do. We can kind of see it, but I'm going to write it out. So we have Fn minus mg, which is down, equals 0. So Fn is equal to mg. And so I can substitute mg here. And then you see what happens is I have an m on both sides of the equation. So if I divide by m, you should do this yourself, right? Watch me and then see that you can do it. You get that. So that leaves a g here. So this, then I have to divide both sides by g. And I get this. So the v squared over r is the AC. So it's v squared over gr or AC over g, either way of writing it. And the AC you got when you answered the previous question. And so that will give you the mu s. And what does that mean? That means if this changes, if this is bigger, then you need a bigger coefficient of friction. And so for this coefficient of friction, if the speed increases or the radius decreases, the thing is going to slide off the turntable as it spins.